Welcome back to The Explainer. Today, we are unlocking the absolute technical magic behind those breathtaking, hyper-realistic video game environments that we all just love to get lost in. We're going to demystify a frankly remarkable master's thesis by Andre Felipe Domingo Silvestre. It was published back in 2017, and it's called A Real-Time Terrain Ray Tracing Engine. Honestly, it is a fascinating look into the sheer computational power and the really clever mathematics required to build our digital worlds. So here's the big question. How exactly do you render a hyper-realistic, seemingly infinite landscape in a fraction of a second and do it entirely without melting your computer's graphics card? I mean, it's a high-stakes computational puzzle. Think about it. When you're standing on a virtual mountain, looking miles and miles into the distance, your machine is frantically performing billions of calculations a second just to figure out what color every single pixel on your screen is supposed to be. Okay, let's dive into this. Section 1. The Quest for Perfect Graphics. You see, there's this eternal war in computer graphics between raw, blinding speed and actual real-world physics. And to understand that battle, we really have to look at the two heavyweight champions of rendering, rasterization and ray tracing. Now, rasterization, that is the incredibly fast norm for most gaming today. It directly projects 3D polygons right onto your 2D screen. But, and this is a big but, it grossly fakes the physics of lighting and shadows. Ray tracing, on the other hand, which was actually proposed way back in 1979 by Turner Whitted, gives you real physics. It essentially shoots millions of tiny invisible lasers, or rays, backward from the viewer's eyes into the digital scene to calculate exactly how light bounces, reflects, and refracts. It's stunningly beautiful, but because of all that heavy math, it is computationally brutal. Which brings us to Section 2. Why terrains break your GPU. Massive virtual landscapes are a unique kind of nightmare for graphics hardware, and it's mostly due to limited memory and massive data transfer bottlenecks. Just picture the sheer, immense complexity of a massive terrain like the Grand Canyon. If we actually tried to store and render every single geometric detail in a scene like that, every pebble, every jagged ridge, every canyon wall, it would instantly exhaust your GPU's video RAM. Boom, done. Some high-resolution terrain datasets have over 20 billion samples. Sending all that geometry across your system's data bus every single frame, yeah, that would bring even a supercomputer to a screeching halt, at least if we aren't incredibly clever about how we structure that data. So to save all that precious memory, engines completely bypass those massive webs of polygons, and instead, they use something called a height map. Basically, this is a special 2D image where each pixel doesn't actually store color, but rather a vertical displacement or an altitude value. It's highly memory efficient. Though I should mention it does have one quirky limitation. Because one pixel equals exactly one height, height maps can't natively map things like deep caves or rocky overhangs. And this brilliantly illustrates how the whole thing works. We start with a stored dataset that just looks like a slightly blurry grayscale 2D image. But then, the engine translates those specific grayscale values directly into altitudes. The bright white pixels shoot up to become high mountain peaks, while the dark black pixels sink down to become deep valleys. Just like that, flat 2D data completely transforms into a complex, physical 3D bumpy surface. All right, moving on to Section 3, the level of detail trick. Now, to actually survive rendering millions of points 60 times a second, graphics engineers rely on a very clever, very old hack called level of detail, or LOD. As a quick refresher, it essentially mimics human vision. Think about it. When you look at a tree from a mile away, you don't actually see the individual leaves, right? You just see a green blob. Well, graphics engines do the exact same thing. Distant terrain is purposefully rendered with far fewer triangles to save on processing time. Then, as you walk closer to that distant mountain, the engine secretly swaps out the low-detail model for a high-detail one. But, as we know, cheating always has consequences. When a high-detail patch of terrain sits right next to a low-detail patch, the underlying math doesn't always line up perfectly, and that causes some pretty ugly visual artifacts. If you're a gamer, you've absolutely seen this. The ground suddenly popping as new textures load in, or literal holes and cracks forming where the different detail levels just awkwardly stitch together. Engineers call these T-junctions, and man, they just completely break the illusion of reality. That takes us to Section 4, Ray tracing meets landscapes. So, the absolute million-dollar question for Sylvester's thesis was this: how do we merge the incredible physics of ray tracing with these sprawling virtual landscapes without completely killing our frame rates? Well, the main hurdle comes down to this staggering statistic. Over 90% of a naive standard ray tracing algorithm's execution time is spent doing one thing, just testing to see if a ray actually hit an object. If you're tracing 1 to 4 million rays per frame and testing them against billions of potential terrain points, the game is literally going to slow to a crawl. The engine desperately needs smart acceleration structures, so it isn't out there checking every single tiny rock in the distance. Now, one very common solution to this is called ray marching. Instead of testing everything, the engine advances a ray in fixed steps across a grid, sort of stepping a line forward bit by bit. At every single stop, it asks, "Hey, did I hit the ground yet?" But it's a really dangerous balancing act. If your steps are too small, the math takes forever. But if your steps are too large, the ray might completely jump over a thin mountain peak, entirely missing a crucial piece of the landscape. To fix that particular issue, researchers created something called cone step mapping. This is a super clever safety zone trick. Basically, the engine pre-calculates inverted cones of completely empty space hovering right over the terrain. When a ray enters one of those cones, it knows with 100% certainty that there is no dirt or rock inside, so it can safely skip a huge chunk of empty air all at once. The catch, though, calculating all those cones for a massive, say, 10-mile wide map requires a ridiculous amount of offline pre-processing time. It just doesn't scale well for large, highly dynamic games. Which brings us to Section 5, a new real-time engine. This is where Sylvester decided to just throw out the old rulebook and build a brand new real-time engine from the ground up. His core innovation is captured perfectly in this quote from the thesis. The implemented engine does not require conversion from height maps to polygonal meshes. And guys, this is huge. In normal rendering, a height map is eventually converted into thousands of flat triangles before it ever hits your screen. Sylvester realized that by ditching triangles entirely, he could use mathematical formulas to render smoother, parametric surfaces directly, using a completely different approach to calculate exactly how a ray intersects the ground. So, the crucial point is how this all comes together dynamically. Step 1, completely ditch the triangle meshes. Step 2, instead of those painfully pre-computed cones of empty space, he utilizes a dynamic structure called maximum Mipmaps. This creates bounding boxes of empty space that rays can skip, and it computes so incredibly fast that it happens in real time. Step 3, the engine calculates the level of detail based on the true 3D distance of the ray, instantly, right on the fly. No more pre-computing those clumsy simplified meshes that crack and tear. Let's look at Section 6, the magic of secondary rays. Now, what's really interesting about this is that the engine's true superpower actually goes beyond just the ground itself. It's all about the light. Previous real-time terrain engines barely even tested this because it was universally considered just too heavy for the GPU. But here, once Sylvester's primary ray hits the ground, it immediately casts a new secondary ray straight toward the sun. If that new ray hits a mountain peak on its way up, the engine instantly knows that exact patch of dirt isn't a shadow. It traces physically accurate, realistic shadows in real time, all while completely avoiding those ugly LOD popping and crack artifacts we talked about earlier. And the proof really is in the data. Testing his highly scalable engine on massive real-world altitude datasets like the Puget Sound and the incredibly bumpy terrain of Colorado, the results were absolutely clear. The engine successfully achieved real-time interactive frame rates, generating millions of rays per second, while simultaneously calculating those advanced shadow physics over massive distances. He basically proved that real-time ray-traced landscapes built entirely without the crutch of triangles are highly viable. Which leaves us with a pretty thrilling question to end on. If this level of rendering was achieved back in 2017, just imagine where we're heading right now. As GPUs continue to grow exponentially stronger year after year, will the old fast but fake rasterization soon be entirely eclipsed by these hyper-realistic, real-time ray-traced virtual worlds? It certainly seems like the eternal war between speed and physics is finally coming to an end, with physics poised to take the crown. Thank you so much for joining me on this explainer, and as always, keep your curiosity focused.